Hi, so good afternoon, good morning, ladies and gentlemen, and welcome to your SETI Institute Colloquium series. Today it's a great pleasure to introduce Peter Michelson. Peter Michelson, full title is a Luke Blossom Professor in the School of Humanities and Sciences, but he's also the chair of the Physics Department at Stanford University, a university not too far away from us, as you know. So Peter is an experimental and observational astrophysicist with a current focus on observations of high-energy universe with the Large Area Telescope, called LAT, on the Fermi Gamma Ray Space Telescope. Historically, he has also done research on gravitational radiation detection, and currently he leads the international collaboration that built and operates the Fermi Large Area Telescope. His investigation includes observation of gravitationally compact objects such as neutron stars and black holes, as well as searching for signatures of dark matter in the diffuse radiation and the study of transient gamma ray bursts. Peter was elected in 2013 as a member of the American Academy of Arts and Sciences, which is the leading center for independent policy research. During this talk, entitled Exploring the Universe, some of the recent results from Fermi-LAT, Peter will give an overview of discoveries that was done with LAT and offer speculation of what may be found next, including possible sources of radiation or radiation. So please join me in welcoming Peter.
So I have to say a little bit, fill in a little more detail about the introduction that was given about me that said I'm an astrophysicist. Actually, that's, I've evolved into an astrophysicist. I actually started out in condensed matter physics, studying the Josephson effect, and you might wonder, what does that have to do with what I'm going to talk about today? And I think, for me, it was just sort of like what happens when you kind of follow your nose. And so I started out doing that and working on the Josephson effect and something called the pair quasi-particle interference current, which was a prediction that Brian Josephson had made. It was actually the original prediction he made. What he got the Nobel Prize for was, in fact, the Josephson current. But anyway, that's a lot of detail. But that sort of work led me to collaborate with a group at Stanford on gravitational wave detection, because we're applying that technology to build very sensitive amplifiers and transducers to detect very tiny vibrations in a large aluminum bar cooled to ultra low temperatures. And these excitations of this 5-ton aluminum bar, which was vibration isolated and so forth, we were looking for excitations due to the passage of a pulse of gravitational radiation from the collapse or coalescent collapse of a massive star somewhere in our galaxy or beyond. So anyway, it turns out that particular approach to detecting gravity waves was justifiably, eventually other technology caught up, and today we have the LIGO experiment, and hopefully in the future there'll be something in space called LISA, which uses optical interferometry to detect gravitational radiation. And the main advantage of that is very long baselines, and the sensitivity improves dramatically with the baseline. So anyway, the reason I mention all that is I'm going to come back to gravitational waves during this talk, because that's always been my true love, but I sort of gave up on it for a while because it was too hard, and I thought, well, I want to actually measure something someday, and I got interested in sources of gravitational radiation, namely neutron stars and black holes and other exotic, they're less exotic today, but 30 years ago they were fairly exotic, and today, we observe black holes and neutron stars. And one of the primary ways of observing them and the dynamics of what's happening to matter and in the vicinity of a black hole or a neutron star is through gamma ray astrophysics. Gamma ray, these objects generate or are responsible for the generation of high energy radiation in a number of astrophysical scenarios. So that's kind of where my interest came from. So let me start by getting the slides going here. So I'm going to only touch on a few results from Fermi that I think are interesting, that personally interest me a lot. But I want to start with sort of a simple statement that I think is really important, particularly in the current epoch of exploration of the universe. And that is to really understand the universe, never mind even talking about a multiverse, to understand the universe and its origin and its evolution, we need data from across the electromagnetic spectrum, from radio to gamma rays. And we need also to study cosmic rays, very high energy charged particles, that also carry information about our universe. And we need to measure these with better and better precision. And eventually we need to, and we're starting to see new windows open, new channels of information. And there are really two that I think are most important in the current epoch. One is gravitational radiation, and the other is neutrinos. So I like to show this picture here, which this is the strip you see there is the galactic plane viewed optically. And that was our view of the universe until, except for the last 50, 60, 70 years. But because of technology development, because of curiosity, we've been able to open up this view and view the electromagnetically from radio to high energy gamma rays. And the information we get is different and complementary in all these channels. So I think this is an important thing that really I think the astronomical community understands, and certainly to explore the universe in depth, we need all of this information. So I've focused in the last 20 years on gamma rays. And the gamma ray sky, which you can see here, the spectrum, this is radio at this end, gamma rays at that end. And the Fermi Large Area Telescope covers a significant part of this spectrum at this high energy end. It is also complemented by the highest energies. Very, very high energy gamma rays will induce showers in the Earth's atmosphere and can be studied using what are called air-Cherenkov telescopes. And there's a new array called the Cherenkov Telescope Array that is led by a European collaboration that will probably come online in the next, within 10 years. But right now, I'm going to focus on what we have learned from observations in this part of the electromagnetic spectrum. And one of the messages is just about everything we've done is complemented and by complementary or simultaneous observations in some cases in the rest of the electromagnetic spectrum, particularly in the radio part of the spectrum and optically. And so with what's interesting about the gamma ray spectrum part of the spectrum is that it offers us a tool for studying, among other things, very powerful particle accelerators that exist in the vicinity of black holes and neutron stars. And it also provides us an opportunity to look for new physics. And in particular, the nature of dark matter and to study matter in extreme environments, and possibly even someday signatures of quantum gravity. So let me, in this talk, I'm going to give you, I can't resist the fact that I used to be an experimentalist. I actually go in the lab and use screwdrivers and soldering irons and stuff like that. I haven't done that in a while, but I want to start this talk by giving you an overview of the principal instrument on the Fermi Observatory, which is known as the LAT, the Large Area Telescope. And also to show you sort of how the instrument design evolved, and the fact that when we launched it, we met all the NASA's performance requirements. But today, the instrument, by design, is actually working better scientifically than it did when we launched. And I think there's some important lessons there. I just want to share with you how that came about. Then I'll turn to the gamma ray sky, and I'll talk a little bit about indirect searches for dark matter. But then I want to focus and give you an update on some important source classes among a zoo of things that we've detected. Focus on pulsars, a bit on gamma ray bursts, and active galaxies. So this is the Fermi Observatory. It doesn't look like a telescope, but this cube on the top is the Large Area Telescope. Think of it as a particle detector, and the particles it's detecting, it detects cosmic rays, and it detects neutral particles, photons of very high energy. By detecting the photons and determining the direction in which they came, measuring their energy, we can form an image of the sky at very high energies. The field of view of this instrument is enormous. And in fact, every 3 hours, every 2 orbits of the Earth, this instrument's in low Earth orbit, every 2 orbits of the Earth, we have roughly image the entire sky with uniform exposure, as I say, every 90 minutes. And this instrument is complemented by a smaller instrument called the Gamma Ray Burst Monitor, or GBM, which works in a much lower energy band from basically hard X-rays, 8 kilovolts, up to about 40 million electron volts. The LAT works from about 20 MeV up to more than 300 GeV, and I'll show you more details about that in a moment. This instrument was developed, and I want to acknowledge the participation and the critical support of collaborators from around the world. And in the US, it's been supported by NASA and the Department of Energy. That's a whole story in itself, which I won't get into, but we have collaborators and agencies supporting us in France, Germany, Italy, Japan, and Sweden. And so we function as an international team. We share in the science. We share in the responsibilities of operating the instrument. And I think even more important, the data all goes public. So you in the audience, if you want to work on Fermi data, you're free to do it, and you can get help. And the help mostly comes from Goddard Space Flight Center, who are our collaborators as well as the hosts for the Fermi Science Support Center. So anyway, this is a picture of this collaboration at one of our collaboration meetings a few years ago in Japan, and it's a large number of universities and national labs and so forth. So I want to acknowledge again their important contributions to the success of this mission. Okay, so enough of that. Let me now say a little bit about how this detector works. So just focus on this, forget all these pictures. The instrument consists of, inside that gray cube I showed you, underneath the hood, there is a modular array of detectors that look like this, that consist of a stack of position-sensitive charged particle detectors. So if a charged particle passes through here, each one of these planes will register where the particle went through, and from that we can then, if we have a way of triggering this instrument, which we do, we can read this out and reconstruct the path of a charged particle that went through. Now, we're not interested so much in the charged particles. We're interested in neutral particles, gamma rays, that enter the instrument, and somewhere in this stack, they interact with matter, as shown here, and a gamma ray, by a quantum electrodynamic process in the vicinity of a high Z nucleus, is converted into an electron and positron. So we don't detect the gamma ray. We literally detect the charged particles that were created by what is called pair conversion in the material in this stack. So once we have these charged particles, they proceed down through the instrument, and we can measure their direction by measuring these tracks, reconstructing where the gamma ray came from, and with what we call a total absorption, a calorimeter, the charged particles enter this calorimeter, they lose energy there, which turns into light, scintillation light, and by measuring the intensity of the flash of light that occurs in here, we can measure the energy of the gamma ray. So we measure the energy and the direction and the arrival time. And we do it one photon at a time. So this is actually a schematic of what that instrument looks like. This is it on top of the satellite just before launch back in 2008. And it was successfully launched, and it's been in orbit now for 6.5 years. So the science we do with Fermi covers a very broad range of energy scales and angular scales and time scales. So on the shortest time scales, we study solar flares and gamma ray bursts, and also something closer to home, there's some work that's been done on what are called terrestrial gamma ray flashes associated with, looking down from above. We, in fact, see flashes of high energy gamma rays. Those occur on a very short time scale. On the longest time scales, we're looking in largest angular scales. We study isotropic radiation from the entire sky, and we're also looking for signatures of dark matter. Now, the reason I show this is that the background rejection required, we're doing this in the presence of an incredibly larger flux of charged particles due to cosmic rays. And cosmic rays are also interesting, but that's not the primary purpose of this instrument. It's to study gamma rays. And we focus on the gamma rays because, in principle, it's astronomy. A gamma ray, you can point back and you know where it came from. A cosmic ray, between the source where it's generated and us, all kinds of stuff can happen. Magnetic fields can change the path and so forth. So gamma rays, cosmic rays are complementary, but it's not the primary purpose of this instrument. So anyway, so we try to reject those. And the algorithms we use have to be most efficient, have the highest signal to noise for these kinds of sources. But on short time scales, it doesn't matter so much. So we can relax the background rejection criteria, and that actually gives us more effective area and sensitivity. So we have this ability to optimize the analysis to fit the source class we're looking for. And this is something that, in fact, the user community can do as well. We provide the tools to do that. Okay, so what do we get from this? Well, this is sort of an iconic image. This is 5 years of data above 1 GeV. It's a map of the gamma ray sky dominated by this bright band across the middle, which is the Milky Way. The center of the galaxy is located here. The anticenter is over here. And you see a number of bright sources off the galactic plane, and most of those are distant active galaxies. And I'll say, again, more about that as we go forward. There's also a diffuse glow, which comes from all directions in the sky, and that's, I'll say more about that as well. Now, before I get into the science, I want to say a little bit more about the instrument. And this gets perhaps a little technical, but I'll try to move through it quickly. I mentioned at the beginning that this telescope is now operating as a scientific instrument better than when we launched it. And the reason is software and understanding, having it in orbit, understanding its performance, tuning the performance. And in fact, we planned this before launch, that we would do a major revision of all the analysis software, the so-called reconstruction code to reconstruct the pair-converted events and extract information about gamma rays. And that effort went on, was a large effort involving that international collaboration, went on for about 4.5 years. And it finally came, we got it done. The validation of it was complete. We call it Pass 8, but that's a detail. It was now released to the community about a month and a half ago. And I think we're going to see, just from the data that's already archived, the reprocessing of it, we're going to see some new science results come from that. And I'll share a few of those with you. So this is where we go forward from. And I won't go into the details of exactly all those improvements. But this shows you one example. This is the acceptance of the instrument. It's effectively the effective area times the field of view. This is pre-Pass 8, and this is Pass 8 is in red. And at low energies, this is the ratio. And at low, this is energy, so this is a GeV 10, 100. That's a TeV up there. So above 100 GeV, there's certainly by a TeV, there's a factor of 2 improvement in the overall performance. At low energy, it's even more dramatic. An order of magnitude improvement at about 30 MeV. And that turns out to be important for some of the science. So we have a new instrument in a way. This is an example of some actual data from a very familiar source called the Crab pulsar. This is a detection of the Crab pulsar. You can see it pulsing. This is from 30 to 60 MeV and 60 to 100 MeV. This is Pass 7. This is the same data reprocessed with Pass 8. And you can see there's a dramatic improvement similarly here. So this is just one example of many of the kind of improvement we've gotten from archival data. But it's also important in the future for the data that comes in, particularly for gamma ray bursts. The detection of gamma ray bursts is also significantly enhanced because of these improvements. And that's important in real time because gamma ray bursts are essentially useless unless you get a redshift, in my opinion. And we need to, the more triggers that we can have that are reliable in the future, then we have the ability to pass that on to the optical community to look for a counterpart and get a redshift. I'll skip that. Anyway, so back to this map. I'll just now take you on a little tour of some of the sources in the gamma ray sky. Now, another point, that this is actually rather old. It needs to be updated. But the thing about Fermi that I think is the most significant characteristic of the high energy gamma ray sky, the sources, is they are time dependent. And you can see that this is essentially raw data projected on a sphere that's rotating. So it's the sky, 4 pi steradians projected on a sphere. You see the galactic plane, but you see these sources, and if you look at them, you'll see that there are flaring sources. See that guy flared on and off. There's one down here. This is a common characteristic of the sky. You also see some sources moving across the sky. See that guy moving across there. So well, you're supposed to ask me questions, but I always like to ask at this point, what do you think that is? It's the sun. Well, Pierre knows the answer, so you're cheating, Pierre. No, I actually showed this at an institute in Toronto several years ago, and somebody said, "Oh, is it a Russian satellite?" And no, but anyway, okay. So the point is, the gamma ray sky is incredibly time dependent. So Fermi should really be thought of as an imaging all sky monitor on time scales, literally from milliseconds for gamma ray bursts, some gamma ray bursts, to days, months, years for active galaxies and other kinds of sources. So this is kind of a map of, summarizes a number of discoveries made with the Fermi Gamma Ray Space Telescope, the Large Area Telescope in particular, from a galactic scale to extragalactic scale. And they're sort of categorized here by source class. So I've mentioned some of these already, but I'm going to go through this and just highlight a few things, okay? So let me start with something that I think goes in and out of the news a lot, and that is the search for dark matter. This is an incredibly important and very difficult investigation that involves, first of all, we don't know what dark matter is. That's a big disadvantage. We think it's a particle, undoubtedly probably is, but who knows what it is beyond that. It could be an axion, it could be a WIMP, it could be, there's a zoo of things. And Fermi has the ability to search for gamma rays that, from possible mechanisms of gamma ray production involving dark matter. So we are on the lookout for this. The simplest thing to detect would be a gamma ray line, but we have not seen any convincing evidence of line emission at all. There was a flurry in the news about a year and a half ago, not from our collaboration, but from the public data archive of a possible line detection. But that since been tracked down, and that is no longer believed to be correct. But beyond that, there are also careful looks for gamma ray emission that don't produce a line, but produce an excess, particularly from the galactic center region. And this is something that we've been focused on. One of the, this is supposed to be the galaxy and a simulation of what dark matter would look like. So the galactic center, there's lots of dark matter there. We know that has to be there. We don't know the exact profile, but we know there's dark matter there. As the density goes up, if there's a channel for annihilation, then that would produce gamma ray radiation, then the gamma ray radiation would go up like the density squared. And so the galactic center is a good place to look. The problem with looking there, the galactic center is a messy place and it's full of all kinds of other stuff, some of which is actually interesting, such as the supermassive black hole there. Anyway, I'll get to that. But across the gamma ray sky, if I take that all sky map I just showed you, that one of the things we do for the community as well as for our own science is to simply analyze it to look for localized point sources. This is the second catalog we put out, which had about 1,873 sources, a huge number of different source classes, galactic, extragalactic, and so forth. And we just recently put out the third such catalog based on 4 years of data. So and this shows the evolution of the catalogs. The latest catalog, we call it 3FGL, Third Fermi Gamma Ray Large Area Telescope Catalog, 3FGL, 4 years of data, has over 3,000 sources in it. And there are a variety of source classes. You may not be able to read this, but pulsars are a large component of that. But a significant part of this is also unidentified sources. About 30% of the gamma ray sources in the sky are still unidentified. And even though we have more sources, the fraction that are unidentified doesn't seem to change. Now, in part because we've done a lot of work on the brighter ones that were detected early, and we've actually gotten some source identifications. But there's still a large fraction that we need multi-wavelength work to nail down what they actually are. Okay, so here's a list of all of the different kinds of sources, and I'm not. You can look at this later. So one of those source classes, which is the largest identified source class, is in fact active galaxies, and this was, I think, anticipated at the time we launched, but the number has exceeded what we thought we would detect, in fact, across all the source classes. So active galaxies, there are over 1,500 of the high latitude sources off the galactic plane, because the galactic plane gets confusing. So just restricting this to off the galactic plane, 98% of these, a huge fraction are active galaxies, and 98% of them are blazars. Now, a blazar is an active galaxy, has a supermassive black hole at its core, 10 to the 7 to 10 to the 9, or in some cases even perhaps 10 to the 10 solar masses, that is interacting with the galaxy around it. And that interaction can produce high energy radiation across, in fact, radiation across the electromagnetic spectrum. And in particular, high energy radiation. The high energy radiation turns out to be typically associated with a very high speed relativistic jet that is created by this rotating, spinning black hole, and it can accelerate particles to relativistic speeds, and those will, in fact, that acceleration process generates radiation as well. So the radiation is beamed in a jet, and those sources are called blazars. And in addition, there's also sources seen at very high energies, above 10 GeV. So we can do we've produced a catalog of such sources. There are about 514 in that catalog, and it looks something like this. Many of them are blazars. Many of them are, in fact, still unidentified. And this is, in fact, a list of sources that only appear at high energies in this catalog and are not present in the lower energy source catalog. So they're very interesting sources. We are working on a revision to that based on 6 years of data. It has about 350 sources in it, above 50 GeV. These are going to be very important to be followed up by the ground-based air Cherenkov detectors that, in fact, work best above 50 GeV. So we'll be working with that community as well. Okay, so let me now turn to some of the items on this chart. Let me again summarize dark matter searches. As I said, to date, despite experimental investigations, I think Fermi's one of them that are of the highest quality. In our opinion, and these have, Fermi surpassed our expectations for its performance, and we've improved it recently. But we do not believe, and I will state this uncategorically, we do not believe that the present data can support a confident claim of direct dark matter detection. That's our position on that, in case anybody was wondering. Okay, but anyway, having said that, we're looking, and we're trying to look very carefully. So there are a number of places to look. Dwarf spheroidal galaxies that are in the vicinity of the Milky Way galaxy, which from measurements of their rotation curves and so forth, other indirect measurements, have large amounts of dark matter. So the mass to light ratio is anomalously large. Those are good places to look. The Galactic Center, as I've mentioned, is a good place to look, but it suffers from large backgrounds and foregrounds. And I've talked about annihilation lines. So let me just say a little more about dwarf spheroidal galaxies. There's been recent breakthroughs, which I think are actually important, from the Dark Energy Survey collaboration, principally at Fermi Lab, but it's a worldwide collaboration. And one of the products that comes out of that, they have detected new, previously undetected dwarf spheroidal galaxies, and they announced 9 new galaxies, dwarf spheroidal galaxies, in the vicinity of the Milky Way back in about January. And we work with them, and we've actually put out a paper on looking for, discussing gamma ray emission or potential gamma ray emission from these dwarf spheroidal galaxies. If we saw gamma ray emission from a dwarf spheroidal galaxy, one would still have to prove it wasn't just conventional astrophysics, but it would be a prime candidate for emission due to dark matter annihilation. So that's the origin of the interest. So we didn't report any detections. One of the sources which we wrote a paper about, Reticulum-2, had some evidence, but not statistically significant evidence of gamma ray emission. So what's needed, there's two things that are needed. One, more exposure, and two, as DES and other surveys go forward, we expect many more dwarf spheroidal galaxies. And this is important for follow-up in the future, because I think there's a very good, if I had to bet, I would say if we're going to see dark matter with Fermi, it'll probably be from dwarf spheroidal galaxies long before anybody believes something from the Galactic Center. But anyway, okay, I'll skip that. We're also, as I mentioned, looking at the Galactic Center region, and as I've told you, that's a very complicated story because of foregrounds and backgrounds. We're sitting over here. We're interested in the gamma ray emission from this region, say the inner kiloparsec, but you don't get to, you have to look through the galaxy in front, and the galaxy behind is shining through. So you really have to understand this emission and that, and then look for any residual that's left after you think you've modeled that. And there's been an effort underway for a long time to quantify our understanding of that, and we have a paper that'll be out very shortly, and we're not reporting the detection of dark matter in that paper. I'll tell you that. Okay, well, let me go on, say something about what I would characterize as my favorite source class. It's a personal statement, pulsars. And here, I think there have been a number of surprises that started back in 2009. It's the cover of Science when we first published a series of papers about Fermi gamma ray pulsars. And to date, well, this all started back, the very first paper we published in late 2008, 3 months after launch, was this object here was known from the CGRO egret days, but it was an unidentified source. With Fermi, with a few months of data, we were able to do a blind search and detect gamma ray pulsations from that source. In the past, we always had to rely on a radio solution. Radio astronomers would tell us there's a pulsar, it's rotating, and more important than the fact that it's rotating in its period is how fast the period's changing, because these sources lose energy, they spin down very slowly. So in gamma rays, it's very hard to directly detect that because there's so few gamma rays. But with Fermi, we have enough area and enough sensitivity that we can afford to search without any hints from the radio part of the spectrum. So this source was detected there. This was back from a paper in 2008. Very significant detection. Turned out to have a period of 315 milliseconds. This was not possible with egret, and we've done it with Fermi. Not only that, we've done it over and over again. So this is where we are today. In fact, I will state, none of my theoretical friends are in the audience. But you know, before we launched, I said, tell me how many pulsars you think we're going to see. And the optimist said 50. In the previous, I don't know how many decades of gamma ray astronomy missions and so forth, egret detected 7. And they said, oh, probably 50. Well, we're up to 160. We're actually closer to 200, but, and there, as I say, there are more on the way. So that was a bit of a surprise, but I think the biggest surprise was the large number that were radio quiet, the ones in blue. Those are only to date seen to be pulsars in the gamma ray channel, not in radio. And also there are a large number of millisecond pulsars, and I think that was the biggest surprise, the huge population of millisecond pulsars that emit gamma rays. And so this is a little sort of summary of that story. In 2009, shortly after launch, we had this many pulsars, and 7 out of that number were millisecond pulsars. By 2014, that fraction had grown significantly. And in fact, at present, of all the gamma ray pulsars we detect, nearly half are millisecond pulsars, periods less than 10 milliseconds. This shows the fraction. So, and this is in fact somewhat biased against finding millisecond pulsars because we cannot the sensitivity of blind searches is not good at very short periods. The number of trial factors and so forth, it's essentially almost hopeless to find a millisecond pulsar in a blind search. We need the radio ephemeris and timing solution. So we work hard on that with our colleagues in the radio astronomy community. So what are these things good for? Okay, now I get to my favorite subject, gravity waves. One of the things that Fermi has contributed to, I think in a significant way, and this will continue, is that these millisecond pulsars turn out to be incredibly, some of them, not all of them, but they turn out to be very good cosmic clocks. And they're distributed around the galaxy. Now, if you have a set of really precise clocks, an array of them, and you time them with radio telescopes, and you do this on a regular basis, you can watch them to see if they glitch or if the phase changes, the arrival time of the pulses changes a little bit. And if you only look at one pulsar, you might think, well, there's something funny about the pulsar, it's noise. But if you look at a whole ensemble of them and you see correlations, that one's doing something similar to this one over here, there's something connecting them. And what connects them, what it can connect them, is the passage of a gravitational wave through the galaxy due to, say, the coalescence of a supermassive black hole system in a very distant galaxy, or due to a stochastic background of gravitational waves, perhaps generated in the early universe. Okay? So there are, in fact, now organized campaigns. There's one head in the United States. It's called the Pulsar Timing Array. There's one based in Australia, and there's a European initiative. And these are all coordinated. And what they do is they, first of all, they love finding millisecond pulsars. So that's why they love us, I think. We contribute to that ensemble of pulsars that they can time. And the more clocks they have distributed over the galaxy, the more sensitive they are. And so that, I think that's an important contribution. And it may pay off. They may actually be able to detect gravity waves. Not at all certain, but very worthwhile to pursue. So this is just a summary of the rate at which we're detecting these millisecond pulsars. And this was a bit of a surprise, too. This shows 2009, when we've had the first bunch of them that were found. And these require radio follow-up. So what happens is Fermi will say, oh, there's a gamma ray source over there. We don't know what it is, but otherwise it acts like a pulsar. It's steady emitter, so forth and so on. So our pulsar timing array, our pulsar radio astronomers get busy and they look at it, they do a deep search, and a large fraction of those sources have turned out to be millisecond pulsars. So this is the rate, this shows the number versus time of new millisecond pulsars that they've discovered. And the rate is constant. And we don't, for a lot of reasons, we don't expect this to diminish in the future. So this is good news. Anyway, I should finish up soon, shouldn't I? Okay. All right, I'll skip through this, but this is the first extragalactic pulsar we've discovered, 50 kiloparsecs away in the Large Magellanic Cloud. This guy is the twin of the Crab pulsar, and it probably has the highest gamma ray luminosity of any pulsar ever seen. And that's a fairly recent result. I'll skip that. Okay, let's skip through that. Let me now say a little bit about gamma ray bursts. This has been a long story. I think most of you probably know it. Started in the 1960s with the VELA program, which was a top secret program of the US government to do atmospheric monitoring for nuclear tests. They didn't, well, we don't know if they detected any atmospheric tests. That's part still classified apparently. But they saw bursts of radiation coming from the other direction. And they couldn't reveal that for several years, but at a famous meeting of the American Astronomical Society, they were allowed to reveal to the community that there were these things called gamma ray bursts. The folklore for many years, more than a decade, was they're galactic. And with the advent of CGRO in 1991, I remember because I was at this meeting, in 1992, there was a symposium of the Compton Gamma Ray Observatory, and the instrument on Compton that was equipped to look for gamma ray bursts was called BATSI. And BATSI showed one of their first all-sky maps showing the locations of gamma ray bursts. And they kind of looked isotropic. Well, there were probably 800 people at this meeting. There was a debate about whether they're isotropic and if they are, well, how could they still be in the galaxy, and on and on and on. And there were a minority of what I think some people thought were crackpots at the meeting who said, oh, they're extragalactic. Well, a vote was taken at the end of this meeting during this session, and galactic origin won hands down, and they were wrong. Okay, so anyway, that's I think a reasonably accurate summary of what happened. So they are in fact extragalactic. The energy scales are absolutely extraordinary, and today, I think very good bet that there are two classes of gamma ray bursts. Here's a distribution that's showing the time scale of the burst. And it's bimodal. Some are long and some are, quote, short. The short ones are generally thought to be associated with mergers of neutron-star binaries. The long ones are undoubtedly probably associated with collapse of a massive star. Both are likely associated with the birth of a black hole. Okay? So this has still got to be really nailed down. We don't know this for sure yet. But anyway, that's work that's underway. I should skip through most of this. This is what Fermi has contributed. The GBM, which I've not talked about much, is the primary detector of gamma ray bursts at low energies. The Large Area Telescope has detected a little less than 10% of what the GBM detects, but at high energies. So some gamma ray bursts, not all, have extremely high energy emission. This was not known until Fermi was launched, okay? And what's interesting, I'll skip all this, sorry. Let me come to, this is a chart that shows the redshift. It's hard to get the redshift of a gamma ray burst. You've got to be right on it optically. And so only about 10% of gamma ray bursts do we actually get redshifts for. But this shows them here, the ones that are known. And this is redshift. The highest redshift one is a little more than 8. And this shows what's called the isotropic equivalent energy in ergs. So this dashed line, I should say up front, gamma ray bursts undoubtedly do not emit their energy isotropically. It's beamed, just like the AGNs I talked about, the blazars. Gamma ray bursts undoubtedly do the same thing. But it's a convenient metric to just, you have to multiply this by a somewhat unknown beaming factor to get the actual energy. But this gives you the scale of the energy. The dashed line is the energy associated with one solar mass converted to gamma rays. Okay? So most of them are below that line, but there's a handful, and most of them are large area telescope sources where the isotropic equivalent energy is at or exceeds one solar mass. So what all that suggests, and it's important, that a very large fraction of the energy emitted by this system, it's a large fraction approaching a few percent or more of one solar mass. So you've got some system forming a black hole, and in a matter of a few seconds emits, a percent or two or more of one solar mass of energy. It's phenomenal. So we need to get to the bottom of this. Okay, one last thing, active galaxies, and here I'll stop. I've already showed you this, so I'll just move on from there. But one of the things Fermi is able to do is every day we monitor every one of these sources to see if it's varying in time. And most of them do, mostly in a fairly chaotic, flaring way. They flare in random ways. But there's some that don't. And there's one in particular, I'll skip that. There's one in particular that this one, it's known as PG 1553, which first came to our attention about a year ago, that shows evidence of periodic emission. Now, I'm not going to say it is periodic. Some of my collaborators are absolutely convinced it's periodic, but I think one has to remain a bit of a skeptic about that. But very strong evidence that the emission could be periodic with a period of about 700 days. It's at the very least quasi-periodic. Well, to date, we're coming out with a paper which has more data than this. But why is this interesting? I think it's interesting because it's the only source we've seen in the gamma ray sky that acts like this, with this strong of evidence of a periodicity or a quasi-periodicity. So what is it? I don't know, but I think it could be a jet instability in a jet, or in fact, it could be due to a binary black hole system. That would be the most exciting possibility, because eventually that binary black hole system will coalesce, and what would be driving it, if that's what it is gravitational radiation reaction. Now, I'm not saying that's what it is, but the only way we're going to find out is to keep looking. If this thing just keeps doing that, the probability, the odds that it's a binary black hole system will increase. But at this point, we don't know. Okay, I'll stop there.
Thank you. The floor is open for questions. We have time for that.
I'm wondering why so many physicists believe dark matter must be particles.
I think it requires the least disruptive extrapolation from the physics we know. I think you're probably referring to Mond as an alternative, and there. No. No. Okay.
God knows
what. Right. It certainly, I believe, fits all. The indirect evidence would certainly suggest that it has a particle nature. Beyond what kind of particle is, that's a whole zoo. There's I don't know how many theorists we have at Stanford, but for every one of them, you could probably. They would each come up with at least 2 or 3 different particles it could be, and they'll all be different. But anyway, it's a zoo of things. We don't know what it is, and we just have to pursue all reasonable conjectures till we figure it out. And so it could be a product of supersymmetry, a so-called weakly interacting massive particle. There were those who hoped, and I think there are some who still do, that the LHC was going to reveal evidence of supersymmetry. Well, it hasn't. It may still do that this year and next year and year after with the upgraded CERN. That'll be a very important period. There may be a dramatic breakthrough or not. And there are other possibilities, axions being one, but it's an experimental question. Eventually, we've got to follow all the leads.
Do you have to account for the influence of the Earth's magnetic field on the pair production and where they actually go in their trajectories?
No, actually, we don't. In the lab, we don't need to do that. I mean, it's not a significant effect relative to other errors.
So probably like other people, I'm kind of wondering about those gamma ray sources that are unidentified. And is there a sense in the community that there may be whole categories of astrophysical phenomena that we don't know anything about? Or is there a sense that, yeah, we'll probably map this to known phenomena, but we just haven't yet, and there's a category of some known phenomena that are harder to map, or what? What's the sense?
Yeah, I think my bet would be that they're a member of one of the known source classes. But, that's why we look. But tracking them down, I think that's important. It's 30% of the sources. So there could be something new, but I wouldn't want to conjecture what it could be. We just got to look. And that, by the way, is not just Fermi. That truly is an astronomical problem. that we need optical, we need every tool we can get. It goes back to what I said at the beginning about we need to look across the electromagnetic spectrum to understand our universe. It's not just optical or infrared or radio or whatever.
So could you tell us, for instance, in the future instruments that are coming online, what will be the instrument that could help us understanding the source of these gamma ray bursts?
Of gamma ray bursts?
Of this 30% of...
Oh, the 30% that are unidentified. I think we have two handles on that. If number of them are time dependent. They do not have steady gamma ray emission. My best guess for those, particularly if they're at high latitude, it's a blazar or something. But what we need is monitoring. We need wider field of view instruments, like, for example, LSST. We've done some work with Pan-STARRS, which does some of this. And I think that's a tool, you know, if you can say, oh, it flared in gamma rays. Oh, there was an optical source that flared. And by the way, that's at this redshift and it's this kind of source. Then you know. But unless, so correlating them in time is a tool. I think ultimately what we'd like is, you know, I have to confess, the Fermi Gamma Ray Space Telescope, by most astronomical standards, i.e. optical, the angular resolution is poor. That's true of every gamma ray telescope that's ever flown. It's just partly the physics. It's a challenge, and I would challenge anybody in the audience who wants to figure out how to do this. The laws of physics don't prevent us from getting down to a micro arc second, but nobody's figured out how to do it. Okay, so it would be wonderful to have a very high angular resolution gamma ray telescope, because then a lot of the uncertainty goes away because you make the error box smaller. That's, by the way, why we were able to identify many of the egret unidentified sources, because a lot of them turned out to be pulsars. And the only reason the pulsar guys could look, you know, in the egret days they did some looking, but the error box we gave them in those days was this big, and their radio telescope was that big, you know, on the sky, and they couldn't get that much telescope time to do a deep search, so it didn't go anywhere. I mean, that's oversimplifying a little bit. With Fermi, we got it down to, they kind of match, so they can take their allocated time and just beat it down, and bang, they've been finding millisecond pulsars. So we got to just keep at it.
I was kind of wondering why some pulsars are, or some gamma ray emitters are radio quiet and others are not. And what's the difference in the physics that would account for that?
They're, in particular, the radio quiet gamma ray pulsars. The way I said they were radio quiet, meaning we did not on Earth detect them in radio. But it's really a problem that there undoubtedly are emitting radio waves, but the radio beaming is narrower than the gamma ray beaming. So the radio part of it just doesn't happen to pass through the Earth. The gamma ray beaming, and this is on sound theoretical grounds, the gamma ray beams are much broader. That's one of the things we learned. So that accounts for most of that, in fact, if not all of it.
How do you view the chances of a gravitational wave detection, whether on timescales or between Fermi versus LIGO or other sorts of detectors?
Well, I think Fermi won't detect gravity waves. Fermi, I think, can help, other than indirectly by finding radio pulsars that the radio community can use in the pulsar timing array. I think the best bet for direct detection of gravitational waves is LIGO, advanced LIGO at this point. I think the next best is in a very different energy wavelength band. You know, LIGO is, you know, 100 hertz to 10 kilohertz sort of band. And that's one kind, that's typically the canonical source thereafter is coalescing neutron stars. But the other effort that's well underway, which I think is a longer shot, but it's damn worth taking, is the pulsar timing arrays. And those, the best bet is coalescing supermassive black holes. Have we ever seen a coalescing supermassive black hole system? No. Do they exist? Probably yes. And that's why, you know, we just never seen a coalescing supermassive black hole system.
Yep.
I don't know, have we? He
a
didn't
question.
object, so it must be right. Anyway,
One question about the instrument itself. It's been in space for several years,
6 years, 6 and a
now?
half.
So what's the status of the instrument, and what's the lifetime expectancy? based on what you
The
know?
lifetime expectancy based on the performance of the hardware, this is wood, right? I can knock on wood. I think we've seen no degradation. In the instrument itself, when we launched, we were worried, you know, it's got something like 2 million wire bonds in the tracker. And we were very worried about we had some difficulties with wire bonding on this scale. And NASA was, frankly, a bit paranoid about it, which is good. They're a paranoid bunch, which is good, actually. Because when you get it up there, you can't go fix it. Right. So we did a lot of testing, but we still had some, you know, there was a little bit of this going on. But we had a requirement that no more than, I think it was 2% of the bonds could fail. That was our design goal, to get to that and demonstrate that with testing. To date, we had a number of infant failures in 1 of 16 towers. There's a story behind that, but to date, we've had less than 0.5% of wire bonds fail, and it's very stable now. So the instrument itself is working exceedingly well. The spacecraft is working very well. I think the main concern there, and we see no evidence of degradation, but one of the concerns was about the reaction wheels. And by the way, they're the same manufacturer as the reaction wheels in Kepler and in a number of Air Force satellites and so forth. So that was a real source of concern before launch, because we knew this. NASA knew it, but there was a careful investigation done. Meanwhile, the spacecraft had been assembled, and you know, I said, well, change the reaction wheels. Well, you know, it's not that easy, and costs a lot of money, and so forth and so on. So there was some, I think in retrospect, the right decision was made to do some mitigation of, operationally, of how Fermi would be operated to sort of minimize the stress on the reaction wheels given various scenarios. And to date, we have seen no degradation in the performance of the reaction wheels. Knock on wood. Now, having said that, we have 4 reaction wheels. If one of them fails, it's redundant, okay? If 2 of them fail, it has almost no impact on the science performance, because we're not like Kepler where we have to, it's a very different kind of operation. But we don't want any of them to fail, so far, knock on wood, none of them have failed.
So I'm trying to imagine how you're able to cover the entire sky in 2 orbits with something that only covers 20% of the sky.
No, it's 25% of the sky at any one moment.
Yeah.
And it takes 2 orbits because the poles of the orbit we rock on and off the zenith. So we're pointing away from the Earth, but 30 degrees above and 30 degrees below the zenith on alternate orbits. So in 2 orbits, we get almost uniform exposure of the whole sky, because the instrument's always zenith pointed. So the spacecraft is doing this. Okay, so we have, so does that explain it?
So it's not a polar orbit, but something.
No, it's a 24.5 degree orbit off the equator.
Okay, thank you.
Thank you.
So the spacecraft is in good health, apparently.
Yes.
So you're gonna have to work on this for 6 more years, most likely.
Well, I hope so.
So you're gonna have a coffee mug to remember when you talk here.
Let's see.
And I hope it's gonna last 6 years as well. Thank you very much for your talk. Thanks for coming.
Thank you.